Every single minute, an autonomous robotaxi streams 60 gigabytes of sensor data into its onboard computer, yet a single floating plastic bag can bring the entire vehicle to a complete dead stop. Right now, companies like Waymo are deploying thousands of self-driving vehicles equipped with sensor arrays worth over $100,000 per car. They can detect a pedestrian 2 football fields away in absolute darkness, yet they still freeze at simple intersections. By the end of this video, you will see the exact invisible atmospheric glitch that tricks $1 million sensor stack into seeing ghost obstacles that do not exist. To uncover why these autonomous systems fail, we have to examine the triple-layer sensory network that replaces the human brain. Over the next few minutes, we will break down how high-resolution cameras, laser-based LiDAR units, and millimetric radar work together to build a real-time 3-dimensional map. You will discover why combining these 3 signals creates a massive engineering paradox where sensors actively contradict one another. And later in this episode, we will reveal the secret fallback mechanism companies use when these supercomputers give up entirely. The first line of sight for any autonomous taxi relies on optical cameras mounted around the roof, mirrors, and front bumper. Modern robotaxis place up to 30 high dynamic range camera sensors across the body to provide a 360-degree field of view. These cameras operate just like human eyes, identifying lane markings, traffic light colors, and street signs using deep neural networks trained on millions of real-world images. However, cameras only measure light intensity and color, they cannot directly measure distance or depth without heavy mathematical estimation. Because cameras depend on external light, environmental conditions quickly degrade their precision. Direct glare from a low-setting sun can blind an image sensor instantly by washing out pixel contrast. Driving rain coats camera lenses with droplets, distorting light patterns and confusing object recognition software. If a street sign is partially covered by snow or tree branches, the vision system might misinterpret the signal entirely, forcing the car to fall back on secondary sensors to avoid a collision. To solve the depth problem, autonomous vehicles rely on light detection and ranging, better known as LiDAR. Mounted as a spinning dome on the roof, a LiDAR unit fires hundreds of thousands of invisible infrared laser pulses every single second. These light pulses bounce off nearby objects like cars, buildings, and pedestrians, reflecting back into the sensor's optical receiver. By calculating the exact nanosecond time of flight for each laser beam, the vehicle determines distance with millimeter-level accuracy. The raw output of a LiDAR sensor produces what engineers call a 3-dimensional point cloud. This digital point cloud acts like an active spatial skeleton, mapping out the physical geometry of everything surrounding the vehicle in real time. Unlike cameras, LiDAR is completely unaffected by ambient darkness because it generates its own laser light source. It can effortlessly map out the exact contours of a cyclist riding down an unlit alleyway at midnight. Despite its spatial precision, LiDAR has one critical weakness: it cannot detect color or read text on signs. That is where high-frequency radar enters the autonomous sensory stack. Radar units mounted in the bumpers emit short millimeter radio waves that reflect off metallic and dense surfaces. While radar produces lower spatial resolution than laser light, it possesses one distinct superpower: radio waves pass straight through heavy fog, smoke, and falling snow. Radar also calculates dynamic velocity instantaneously using the Doppler frequency shift of returning radio waves. When a lead vehicle slams on its brakes, radar instantly measures the relative speed change long before camera algorithms finish processing consecutive visual frames. By measuring velocity directly, radar provides an immediate early warning system during emergency braking scenarios. But raw radar signals alone lack the detail to differentiate between a metal trash can and a stalled sedan. This hardware triad creates a massive challenge known in robotics as sensor fusion. Trunk-mounted liquid-cooled supercomputers run custom algorithms designed to merge high-resolution camera images, precise LiDAR point clouds, and high-velocity radar returns into one unified model of reality. If the camera sees a red traffic light, the LiDAR detects an open road, and the radar senses a stationary metallic mass. Sensor fusion algorithms must resolve these conflicting data streams in under 20 milliseconds. When sensor fusion functions smoothly, the robotaxi moves through complex traffic with incredible precision. But when environmental edge cases occur, the entire decision-making process degrades rapidly. The first major failure point involves highly reflective surfaces, like glass curtain buildings or chrome trailers. Laser light hitting a mirrored surface bounces away at an extreme angle instead of returning to the receiver, creating a massive invisible void in the car's three-dimensional point cloud map. The second major point of failure is atmospheric interference caused by water vapor, dust, and heavy road spray. Falling raindrops and airborne steam behave like microprisms that scatter infrared laser beams in thousands of unpredictable directions. When laser light hits dense exhaust fumes or street drain steam on a cold morning, the LiDAR sensor interprets the cloud as a solid concrete wall. The central vehicle computer senses an imminent crash and triggers full phantom braking in live traffic. Construction zones represent another common trigger for autonomous failure due to human unpredictability. Human workers frequently use informal hand gestures, wooden signs, or temporary cones that break standard traffic rule sets. When a flagger signals a vehicle to drive into an oncoming lane around roadwork, the camera vision system registers illegal lane departure while the LiDAR detects nearby barriers. Overwhelmed by contradictory instructions, the software defaults to safety protocols and freezes in place. This brings us to the phenomenon known as phantom braking, one of the most dangerous software failure modes in self-driving vehicles. Phantom braking occurs when sensor fusion algorithm thresholds are tuned heavily toward extreme collision avoidance. If a shadow under an overpass triggers a sudden radar noise spike, the system errs on the side of caution and applies maximum brake pressure. This sudden speed drop exposes the robotaxi to severe rear-end collisions from human drivers trailing closely behind. When internal software algorithms hit a point of high uncertainty, most commercial fleets call upon a hidden human backup network. Remote teleoperation centers monitor autonomous fleets in real time through encrypted cellular connections. When a robotaxi becomes paralyzed by road debris or construction cones, an alert drops onto a human operator's screen miles away. The human operator draws a safe path around the obstacle on a touch screen, allowing the autonomous car to resume navigation. Relying on remote human assistance highlights the fundamental challenge of scaling autonomous vehicles worldwide. While self-driving systems can handle 99% of standard city driving, solving the final fractional percentage of edge cases requires near-human contextual reasoning. Edge case scenarios like fallen power lines, erratic emergency vehicles, and extreme weather continuously push machine learning models past their operational boundaries. Autonomous taxis have fundamentally redefined how machines perceive physical space through the power of camera, LiDAR, and radar sensor fusion. Yet as long as real-world roads produce unpredictable weather, reflections, and obscure human interactions, these automated systems will continue to face complex failure points. Understanding these optical and spatial limits is the key to building safer transportation networks for the future.